Hi everyone. Hi, welcome to this channel once again and hope every one of you are doing very well. Now today our discussion is on the diaphragm, its modeling, its criteria, the structural response in the software like StaadPro and the RAM structural system. And most of you are aware of what exactly is diaphragm. So it's one of the most important structural component in the building structure. So I thought of covering this short content on this. So in general, it seems like diaphragm is a slab of a building. But the term slab is not that structurally specific from its structural behavior point of view, whereas the diaphragm definition is more specific and carries more structural behavior related information. So let's see how the diaphragm are defined and how they are classified with respect to different country code. Here we are taking two different country code. One is the ASCE-7 and another is IS 1893-2016. So one is the US standard and one is the Indian standard. So if we go by the US standard, they are classifying the diaphragm by three different category. First is the rigid. Of course, if it is rigid, it has got the infinitely high in-plane rigidity. The second one is the semi-rigid. It has got in-plane rigidity, but it doesn't have this value up to some infinite level. So it has got some finite amount of in-plane rigidity. Third is the flexible. So from the definition itself, you can assess that the flexible means it doesn't have an infinite stiffness at all. So these are the definition and the classification per ASCE-7 code. Now, if we go by the Indian standard, then the Indian code classifies the diaphragm in only two different categories. One is rigid and one is flexible. There is no definition of semi-rigid in the Indian code. So the rigid is same. It has got the infinitely high in-plane rigidity, whereas flexible doesn't mean that the diaphragm doesn't have any in-plane rigidity. So essentially the semi-rigid of the US code, that is AAC 716, is same as the flexible diaphragm of the Indian code, that is ISO 1893-2016. It is just the name are different in both the codes, but essentially both of them are the same. So here also we can understand the structural behavior in a very simplistic way. Uh, if we take the basic relationship between the applied force, stiffness, and displacement, so it is like stiffness is the applied load over the displacement. So if we take the rigid diaphragm, then my displacement would be zero. That's because the in-plane stiffness, that is the Kr, is infinitely high. So there is no in-plane deformation. If we take the semi-rigid of AAC 716 code or the flexible as per IS 1893-2016 code, then the displacement is having some finite value because the stiffness is also having some finite value. So here the in-plane deformation is present up to some finite magnitude. And the flexible diaphragm, which is under the definition of AAC 7 2016, the displacement is infinitely high because you are having the denominator value of zero. That is, the in-plane rigidity is zero. So of course, for the flexible diaphragm, there would be infinite in-plane deformation. So technically speaking, in the flexible diaphragm, it's like there is no such diaphragm at all which is connecting the frames. These frames would act independently if they are not connected by some other means. So if there is any introduction of flexible diaphragm, that doesn't make any connection in between the two different framing system. So this is the rigid diaphragm per AAC 716 and also as per the Indian code. Now let me play this animation here. So this is one of the floor plan. You can see the floor plan is moving as a whole, just like a rigid body movement. There is no internal deformation at all. And this is the flexible diaphragm. flexible as per Indian code and semi-rigid as per ASCE-7 code. Now, in the flexible diaphragm or the semi-rigid diaphragm, now if you see the deformation of this in-plane deformation, you can see that as there is a significant portion of cutout at the two opposite edges, whenever it is trying to deform, two of the wings are trying to move close to each other, and on the other side is trying to move away from each other. So essentially, you can see that there is some internal deformation and it is not behaving like a rigid body. So there is an internal deformation. That's the reason it is known as the semi-rigid as per US code and the flexible as per Indian code. And then the flexible diaphragm, which is defined under the US code. That means there is no in-plane stiffness in the diaphragm. So if we go by the definition as per ASCE 716 code, if you go to the chapter number 12.3.1.1, the flexible diaphragm condition, what they define it is something like a steel deck which are untopped or some wooden structural panels. These are from the different materials point of view which are permitted to be idealized as a flexible. That means although they have some amount of in-plane stiffness, but these are very much negligible compared to the main structure. For example, a thin or a very flimsy steel deck which is not topped by some concrete, it has some negligible in-plane stiffness. So that's the reason AAC code term those elements as a flexible or the flexible diaphragm. So you can go to this entire chapter to have more clarity on this diaphragm definition. Now the rigid diaphragm as per the AAC 716 definition, it is covered under the chapter number 12.3.1.2. So the rigid diaphragm condition is something like the diaphragm of a concrete slab or the concrete filled metal deck with the span to depth ratio of 3 or less in structure that doesn't have any horizontal irregularities. So they are permitted to be idealized as a rigid diaphragm. That means if any of the conditions are not met, then you can't classify it as a rigid diaphragm. So essentially, if you see from the structural perspective, the code demands that your structural or the slab plan should not be that slender. Higher the slab looks like a slender element, it would have more tendency to undergo the in-plane deformation. And also, if there is a significant amount of horizontal irregularities, the diaphragm can experience some in-plane deformation. For example, significant proportion of the cutout that can lead to a significant amount of in-plane deformation. So this is the third clause, that is 12.3.1.3. That is, if any of the different rules that we have just defined for classification of the rigid and flexible are not satisfied or not applied for defining the diaphragm property, then you can use this empirical rule by which you can ascertain if the diaphragm can be classified as a flexible or not. So here you can see that there is a cutout in between this slab. All you need to do, you need to determine the average displacement of this entire diaphragm. Average displacement means you take the four corner nodes, calculate the displacement, and then average them out. You will get the average displacement of the entire diaphragm and also the maximum displacement of the diaphragm edge, that is the chord. You just determine the ratio, that is the ratio of the maximum deflection and the average displacement. If it is greater than 2, then you are permitted to consider it as a flexible diaphragm. So there is another condition as defined by the code for defining the diaphragm flexibility. It says that unless the diaphragm can be idealized as either flexible or rigid in accordance with the three different clauses that we have just discussed, the structural analysis shall explicitly include the consideration of the stiffness of the diaphragm. That is by modeling with the actual plate stiffness. This is what we call it the semi-rigid diaphragm modeling or the semi-rigid modeling. And code says that irrespective of all the clauses that we have just discussed, it is permitted to model the structure by the actual slab property. So in other words, you can model any diaphragm as a semi-rigid diaphragm if you model them properly with the material property and the sectional property of that slab. So this is the diaphragm condition for the Indian code. Indian code, uh, as we have discussed for the ASCE code, it has also got these kind of similar rules. There is also a ratio, the calculation of the maximum chord displacement to the average displacement. If it is greater than 1.2, then it is considered as a flexible. So Indian code doesn't provide any explicit definition of the rigid diaphragm. So if it doesn't fall under the flexible diaphragm definition, then it conversely come under the rigid diaphragm category. So here you can see the diaphragm condition as far as the plan irregularity is concerned. So here you can see that in a building with the discontinuity in their in-plane stiffness, if the area of the geometric cutout is less than or equal to 50% of the floor slab, then it shall be taken as a rigid, or else it would be the candidate for the flexible diaphragm. And also it says that if the cutout proportion is more than 50%, then diaphragm would be automatically considered as a flexible. So here you can see the code doesn't define the term rigid diaphragm explicitly, but implicitly code says the definition of the rigid diaphragm through its aspect ratio, just like we have seen it for ASCE 716 code. In ASCE 716 code, the definition is much more clear, but here also Indian code has defined the diaphragm definition, but in a very implicit way. So the diaphragm in StaadPro Connect Edition, that is the main point that we are supposed to discuss here. So instead, you can directly define the rigid diaphragm. You have the tools by which you can directly define the diaphragm height, and program would automatically consider the very same flow level with the rigid diaphragm property. On the other hand, if you want to define the semi-rigid diaphragm, there is no such direct tool or direct option by which you can directly define the slab or any kind of flow level as a semi-rigid. But basically, semi-rigid is plate elements, meshed plate elements. So you can model the semi-rigid diaphragm instead by simply going for the plate mesh. Now, this is a STAAD model. If you see here, this is a node. Now, previous to Connect Edition and some version of SS6 and all, we didn't have this float diaphragm, direct float diaphragm option. We only had the master slave. The master slave means you are tagging one of the node from the collection of or from the set of nodes as a master and assigning remaining the nodes as slave. That means you are establishing some rigid link between the master and the slave node. With this approach, we used to define infinite rigidity for a floor to just represent it as a rigid floor diaphragm. In the previous scenario, we used to take any of the nodes within the or within the vicinity of the center of mass, assign it as a master, and rest of them as a slave. But later on, we have directly come up with a feature called float diaphragm. Here, we didn't have to select the node manually, and we just have to define the heights here, height of the floor level, and it will identify that height. And you have two options: either you can select any of the node as master node, or you can use this calculate option. It will calculate if there is any node which is coinciding with the center of mass, then it will take it as a master node, or it will create a mathematical node and which would be at the very same location of the center of mass, and it will be treated as a master node, and all the remaining nodes within the floor level would be treated as a slave node. So this is the basic idea behind this float diaphragm, by which you can directly model rigid float diaphragm instead. So here in this model, I have already created three rigid floor diaphragm at three different heights. You can see it here. Now remember one thing, for modeling the rigid floor diaphragm, you must have to create the reference load. That is very important. So I have created two reference load. There are different kinds of reference load, and in this case we are treating it as a mass reference load case. Mass reference load case means this is treated as a seismic weight or the mass when we are doing the mass modeling for response spectrum. Now please remember that whenever you are creating this mass modeling, don't forget to select the loading type as mass, or else it won't work. It's the same as you define as the load case. In the load case you define your loading and all. Here you are defining the mass in three different directions. For dead load, live load, that means these are the inertial load which will participate when the earthquake activity kicks in. And then you needn't have to do anything else. Just define the seismic definition. This is for the static seismic here. And there is some important things. Maybe I will talk later. Please don't check this box. Why? This is very important. I will come later on, because we are using the rigid floor diaphragm. The rigid floor diaphragm, you needn't have to check this box. Okay. Now, if I go down, I have just defined the seismic action in two different directions. So what we can do here is define the accidental torsion coefficient as per the code, that is generally 5%, that is 0.05. And for the inherent torsion, the natural torsion, I have defined it as 1. In several codes, it says it has been amplified by some factor like 1.5. You can define the factor. Just for this demonstration, I am keeping it as a 1. So once you do it, program would identify. So whenever you define the rigid floor diaphragm, it is able to calculate the center of rigidity and the center of mass. And of course, by this, it finds the lever arm and it can calculate the torsional effect. And also, whenever you're defining the accidental torsion, it will taking the lateral dimension and multiplying it with the percentage that you have defined to find the lever arm and then the accidental torsion. So you can see all those torsional effects has been generated. Now this is how you can define the rigid floor diaphragm. Instead, if you see it here, I have already defined, so no need to define. There is something called floor range and also select. I will come to that later on. So I have already performed the analysis, and before I do the analysis, let me take you to a very important thing here. There is something called, if I go here, uh, there is something, just a moment, yes, floor diaphragm. Now please remember that the current version of STAAD, we have ISO 1893 2016 implemented, and also we have the previous version, previous edition of the code 2002, and also ASCE-7, 5, 10 and 16. Now the beauty of this is, whenever you are checking off this option like check irregularities and soft stories, program can automatically calculate the and check different conditions prescribed by the code to check the irregularity and show you the status, whether it falls under or violating any irregularity rules or not. So in this model, I have already clicked in the irregularity rules and no need to mention it again. So whenever you are doing the rigid floor diaphragm, please don't forget to define this one called print dia CR. This will report you the center of rigidity and the story stiffness. The story stiffness is the vertical irregularities. It will check and report you the story stiffness. So you can see that most of the irregularities, both horizontal and vertical irregularities, as well as the inherent and accidental torsion, can be defined through this rigid floor diaphragm definition. So there is no physical slab, you can see here. So I have already performed the analysis here. Now let's quickly go to this output file. Now in this output file, you can see here, I'll just quickly go through that because I have to cover a lot of important things here. It has performed irregularity checks based on the codal conditions. Okay, so if there is any re-entrant corners and all, the codal conditions means I have already opened the code here. You can see these are the different codal conditions reentrant corners, if there is some the percentage, if or the aspect ratio, and if the cutouts is excessive and all. So these are different kinds of condition, and based on which program would show you the status if it is okay or not. You can see. So going into the detail of torsional and other irregularities, we need to have separate class on that. So it needs a long discussion. So we will keep it for some separate sessions. So you can see the idea is you can see all the different kinds of irregularities program has checked automatically. And finally, the center of rigidity it has calculated, and also the story stiffness. Now there is a very important thing. Most of the user ask us, what about if there is any cutout? Means whenever there is a cutout, then of course that due to this cutout there is no mass, there is no stiffness, so your center of mass or center of rigidity might be affected. So what to do, because there is no physical slab. Now for this, I don't touch this model because I don't want to change in this model. So I have a different model here, maybe in this model. The idea is if there is any cutout, for example, in this model, I am assuming that this panel doesn't have any diaphragm, rigid floor diaphragm. There is an opening here. So if this is the case, then what you can do, you can use this select node option. Now in the select node option, for example, this is the node number 15 and 16. If I go there, let me go to this. Okay, now you can see here I have already deactivated it to just show you. What you can do it, once you click on this, it will be automatically active, like rigid floor diaphragm. Just a moment. This is, sorry, yes, this one. So floor diaphragm dia joints 1 to 14, 17 and 18. Now you can see here I have excluded the node number 15 and 16. So once you have excluded them, that means you are not considering these portion to be included in the calculation of center of mass and center of rigidity. By this way, you can exclude any opening and cutout. And if there is not any closed panel like this, it won't be treated as a diaphragm automatically. So this is the way you can consider any opening, effect of the opening in the rigid floor diaphragm definition. Now, what if the structure doesn't exactly qualify for the rigid floor diaphragm as per the different clauses, codal clauses that I have defined? So there is another option which we call it the semi-rigid, right? Now, semi-rigid diaphragm is like when you are physically modeling the diaphragm with the plate elements. Instead, of course, you can directly model with the plate elements like this by the plate mesh. But there is a very important things to note here, as it has been physically meshed, physically modeled. So how about the inclusion or defining the accidental and natural torsion? Now here you needn't have to calculate or define the natural torsion as an input, because it's a physical place been modeled. So of course, if there is any torsional effect, it would be automatically captured by the program in the analysis phase. But what about the accidental torsion? Now for the accidental torsion, the process is almost same. Just here you need to calculate the include accidental torsion. It is meant for any kind of non-rigid diaphragm. So in this accidental torsion, and another important thing here, just to note it, here you needn't have to define any factor as 0.05 and all. You just define it as a 1. 1 means it will automatically calculate any kind of coefficient like 5% or 10%, whatever, whatsoever defined by the code. 1 doesn't mean it will take 1 as a value. It will take it as an instruction to take the codal provision of calculating the coefficient. So that's the way you can define the semi-rigid diaphragm instead and define the accidental torsion here. Okay, now we will quickly see the different ways and different types of diaphragm that we have in the RAM structural system. Now, as we have already mentioned that RAM structural system is meant for the building-like structure, and it has got some different modes of diaphragm templates where we can choose them, which are required for different scenarios. So we have already opened the RAM structural system, and this is one of the module that is called the RAM frame. Now I have already assigned some diaphragm. You can see these are the different flow levels. I have defined two different flow level type, and just you need to define the floor plan and all, and you can define the story height, and program can automatically generate the flow levels, and it will generate the complete physical model for you. So here we had already defined the diaphragm as a rigid. Now this is the one, and this is the drop down list. Now here you can see the four different types of diaphragm that we have just mentioned a while ago, like rigid, semi-rigid, flexible, and pseudo-flexible. So when you are assigning it as a rigid, then each of the flow level would be considered with only 3 degrees of freedom. That is two in plane, and one is the torsional degrees of freedom whose axis is perpendicular to the plane of that diaphragm. So each flow level would have 3 degrees of freedom. So if we have like 1, 2, 3, 4, 5. So 5 floor means 15 degrees of freedom. And if we invoke the semi-rigid, that means the entire flow level would be meshed and finite number of nodes would be created internally. So again, each of those nodes would carry its own degrees of freedom. For example, 3 degrees of freedom. If there are 100 nodes, then 100 multiplied by 3 would be like 300 degrees of freedom for each flow level. So, why it is important? Because while program is solving stiffness matrix, then you need to first know the difference between these two, and based on this, you can estimate the time that is required for solving this stiffness matrix. If it is rigid diaphragm, then every flow level would be considered with 3 degrees of freedom. So entire degrees of freedom, like all the nodes, internal nodes and all, as they are tethered together by a single, rigid flow. So there is only a single degrees of freedom for each directions. Basically all the degrees of freedom are consolidated into single degrees of freedom along each direction. So for this kind of structure, we have reduced the degrees of freedom significantly from the semi-rigid to rigid. And that's the reason it will consume a little amount of time compared to the scenario where you have meshed the plate and you have used the semi-rigid diaphragm. Now, please note that in RAM structural system, although you have defined it as a rigid diaphragm, still it will include the plate element here. Just the in-plane rigidity would be infinitely high. So if I go to the next option, that is the semi-rigid, then the program would mesh the plates and create the internal nodes for me. For example, this one, if I choose, so I have just regenerated the mesh because I have just changed the diaphragm criteria. Now if I go to view and then go to the mesh floor, now here you can see all the floors seems to be have meshed, but as I mentioned, program considered it's a meshed and meshed with the plate elements. But if it is a rigid, then all the plate elements should be considered to be bounded by a single rigid diaphragm. But here it is like semi-rigid diaphragm, so it's basically behave as a plate elements which can undergo some out-of-plane bendings and all. So it can also undergo in-plane deformation as per the definition of the semi-rigid diaphragm. So basically, this one is capturing the true nature of the structural response. If you have any kind of cutouts, or if you want to consider some in-plane deformation of that physical plates. Okay, so then we have like flexible. Flexible, as I mentioned, it's nothing but some fictitious diaphragm that is being assumed where both the framing system, if they are connected by this flexible diaphragm, they would behave independently. So that's the reason you can see it's shown as flexible oblique none, as if there is no diaphragm at all. And last is the pseudo-flexible. That is the mathematical diaphragm where you can allocate the force, allocate the story shear. So once you assign this, then you can have the option here under the loads. You can uh, allocate the proportion of the lateral story shear to different framing system. Two different framing system means, for example, there are shear walls, as you can see here, and also there is a moment resisting frame. You can assign the shear wall as a framing number one. You can assign it in this program, and you can assign the moment resisting frame as a framing number two. And then you can manually allocate um, the story shear in two different framing system, and program can accordingly take those values and perform the analysis. So that's basically used for the location analysis, which is required for the dual system in the building like structure. So the question is rigid or semi-rigid? So that's a very vital question. Like which type of diaphragm should we take? So the answer is not that straightforward. There are a lot of advantages if you take it as a rigid, or even if you are taking a semi-rigid, then also you can get some benefits. But both of them has some shortcomings, so we will just see it. So depending on those engineering understanding, you have to apply your engineering discretion to select the type of diaphragm which is needed for your structure. So if we take the semi-rigid diaphragm, for example, I have taken this kind of floor plan, and we will just take it with some example in StaadPro. Now here you can see these are some complex shapes of the floor plan. Most of them are open shaped. That means they are not closed. Although these shapes are not that usual, but a lot of buildings might have this kind of shapes, unusual, unsymmetric shape. So these kind of shapes, if you take, for example, these are the one, then these kind of shapes could be used very carefully if you want to assign them as a rigid diaphragm, because they can be very much critical to behave as a semi-rigid diaphragm to capture few of the structural response. So if you assign them as a rigid diaphragm, then few of the structural response could be ignored, which is not good for your building design. For example, let's take this she-shaped floor plan. Now, when you're performing the analysis, what you are intended to obtain from the analysis, you are intended to get the responses like forces, movement, reactions, displacement, and also if it is for any kind of seismic action, then you are also intended to capture its mode shapes. Now, in this kind of structure, if you see this kind of floor plan, as these are not closed, if you see this panel or if you see this plan, they are not closed. So after performing the analysis, some of the modes you might encounter, you might experience that they are trying to come close to each other. That means these two extended these two extended wings try to come close to each other. That means it is not behaving as a rigid body. A rigid body means this she-shaped plan would have displaced as a single rigid body movement. But as there is no such a link in between these two wings, and also these kind of floor plans are very slender, so there could be a significant amount of internal deformation, and this kind of deformation may lead to some significant amount of internal displacement. For example, these two extreme end of these wings, so when you are assigning it as a rigid diaphragm, then after performing the dynamic analysis, the eigen solution could not capture any of the mode which is having this kind of open and closed mode shapes. That's because we are treating this floor plan as a rigid. But in some cases, these kind of mode shapes could be very much significant in the sense that this mode case could carry a significant proportion of mass participation factor, which you must consider. So you need to just use your engineering discretion to just check the shape and the geometry of this floor plan. If it looks very slender, very flimsy, and if it looks not that compact, just like this, quite kind of open-ended, then you might want to use the semi-rigid diaphragm. So this is one of the model that I have taken. This is a floor plan which is having a shape of the letter T. It is quite slender floor plan. Now, after performing the dynamic analysis, now here you can see the two wings of that floor are just moving in the opposite directions. So they are trying to get some internal deformation at one edge, and on other edge it is experiencing some tension. So this floor plan has got this kind of mode shape, and you can't even ignore this mode shape because you can see here it carries around 70% of the mass participation factor. So had it been assigned with the rigid diaphragm, then you would have ignored this important and critical modes. Now, here is another example. This is somewhat like a building which is having like the shape of a letter Y. It generally exists for any office building and also some hostel or any kind of public utility building like a hospital and many more. So you can see these are two wings and we have a central block. So after performing the analysis, let's investigate the dynamic response. Now, now here too, you can see that these two wings are also trying to behave like a semi-rigid diaphragm because you can see they are trying to uh, undergo through some internal deformation, in-plane deformation. So if you also take this the mode participation factor for this one, here you can see this is the shape of these two opposite wing. You can see it's open and close mode because you can see two wings are trying to come close to each other and then again try to recede from each other. So that's not the behavior of a rigid mode. Rigid mode is like the entire floor plan would move as a rigid block. There won't be any kind of internal deformation. But you might be wondering that is that mode quite significant? That can be understood if you see the mass participation factor of that mode. So here too, you can see that mass participation factor is around 33%. So you can't ignore this mode. It is carrying a significant proportion of the mass. So uh, you must use the semi-rigid diaphragm for this kind of structure, this kind of floor plan. Now let's take another example. This is like slab with a cutout. As you have already seen on the US and as well as the Indian seismic design code, where it discourages to have some significant proportion of cutout area because more you have the cutout, more your structure would behave as a very flexible kind of, and it is not that much symmetric in the sense. So in this case also, if you have the cutout like this, and this is mostly used for the cutout where your lift core is running through, and by any chance you have the cutout like this, and you have shear wall like this, and you have assigned the entire floor as a rigid floor diaphragm, and due to the lateral action, as there is a significant portion of a gap, this portion might undergo through some internal deformation depending on the span and the size of the cutout and the thickness of the slab. So if you assign it as a rigid floor diaphragm, then any kind of internal element, like here you can see here, internal element here is the concrete shear wall, they won't experience any kind of in-plane action like in-plane stress. That's because you are analyzing it by assuming that entire floor would behave as a rigid floor. So any kind of internal deformation that would have transferred the stress to that shear wall would be ignored if the rigid floor diaphragm would have been assigned. So in case of semi-rigid diaphragm, as a semi-rigid is nothing but it's a real analysis of the plate element after it has been generated with the plate mesh. So it would capture the actual structural response, and these kind of internal elements like shear wall and all would be calculated with the actual stress that it is supposed to experience. Now let's take a third example. That is mostly very much relevant to the steel structure, uh, and it's mostly used in the industrial setup. For example, you have the horizontal bracing like this, which is just resting at the bottom of your diaphragm. Now, let's take this scenario. So this is a example model which is very much relevant to the image that you have just seen. Now, this is a simple frame structure where I have defined the diaphragm for this entire top slab. And you can see there is no physical slab. Instead, as I've mentioned, if there is no physical slab modeled by the plate element, it is not the candidate for the semi-rigid diaphragm. So here we have already assigned the rigid diaphragm for this floor level. Now here you can see we have several horizontal cross bracings. The purpose of these cross bracings are to resist any kind of lateral deformation of that entire floor plan. So after analysis, you can see here that in first situation, there is no such rigid diaphragm being assigned, and you can see a significant amount of axial stress experienced by these cross bracings. Now let's add the diaphragm in that very same floor level. I have already created the diaphragm definition. I have just inactivated in the previous scenario. Now I will just get them activated. Now here in this model, the physical rigid floor diaphragm is there, and after analysis, let's see the forces in these cross bracings. Now here you can see no forces have developed in those cross bracings. That means all the lateral forces and all are taken by the diaphragm itself, because you have defined it as a rigid diaphragm. As the rigid diaphragm, you can't expect any kind of internal deformation. That's the reason any kind of member which are connected with that rigid diaphragm in the very same plane won't experience any kind of axial deformation and all, and that's the reason they won't attract any kind of forces. But that is not the real case in the real life scenario. Every diaphragm has got some finite stiffness, in plane stiffness. And for example, in this case, if your diaphragm is not meant for the rigid diaphragm and you have created all those horizontal cross bracings just to resist any kind of lateral deformation, then the purpose of these cross bracings have been defeated by this introduction of this rigid floor diaphragm, because here these cross bracings have not carried any proportion of the actual forces, so they have got no role here. So there is absolutely no point in adding those cross bracings if you are assigning the rigid floor diaphragm. So for this kind of situation where you are adding the cross bracings to impart some kind of resistance to the structure against any kind of horizontal in-plane deformation. So use the rigid floor diaphragm very judiciously, very carefully, because they can attract all the forces, and by doing this, you would bypass the forces that would have actually been transmitted through those cross bracings. So that's not the actual capture of the structural behavior. Here you can see these cross bracings are not experiencing slightest of the axial forces. So this is another example of the cutout. For example, you have a floor plan like this, and this is the open portion, and somehow you have introduced a beam to resist this internal deformation. But if you assign this floor with the rigid floor diaphragm, then these beam won't experience axial deformation, and thus it won't experience the actual axial stress which it's supposed to experience in the real life scenario. And then another scenario where the stiffness of the diaphragm would really impact the calculation of the base shear. Now, here you can see this is the graph of the natural period versus spectral acceleration, which is used to calculate the acceleration response. And then you need to combine all those responses for the respective mode shape and combine them with different methods like CQC or SRSS method. Now, the idea is like these spectral acceleration is dependent on the natural period. And the natural period is again dependent on the stiffness. So while program calculates the natural period, or the natural period is nothing but it's just an inverse of the natural frequency. So after performing the analysis, after solving the eigen solution, um, the program would determine the natural frequency and then the natural period depending on the stiffness of the structure, mass and the stiffness. Now, if you define the rigid floor diaphragm definition, then the infinitely high rigidity of that diaphragm along the in-plane direction would be considered. Whereas if you define the semi-rigid diaphragm, then you are going to define with the actual rigidity of that slab in the in-plane direction. So in both the cases, you have a difference in the rigidity. So that would impact the calculation of the natural period or the natural frequency, and invariably it will affect the calculation of the spectral acceleration and then your base shear. So here you need to judiciously use your engineering discretion to define the floor diaphragm as rigid or the semi-rigid. Now the transfer slab. Now this kind of transfer slab could be very common in the modern building. Now, the definition of the transfer slab is like this, just a very simple definition. You can see here the columns are resting on the slab, and just below that slab, there is no column. That means at that particular junction. So that slab would transfer the load of that column through its out of plane shear, and then it would transfer to the nearby columns. So instead, if you model it by the rigid diaphragm, then you are not going to capture the true behavior of this transfer slab, because in the rigid diaphragm, instead, there is no assumption of the physical plate elements, right? You are just defining it as a mathematical linkage between a few nodes by the master and slave relationship. So instead, you have to model it by the plate elements, and when you are modeling it by plate elements, you are assuming it to behave as a semi-rigid diaphragm. Whereas in RAM structural system, you can model this transfer slab both by the rigid as well as the semi-rigid definition. That's because in RAM structural system, both in the rigid and the semi-rigid, the plate elements are considered. Even in the rigid diaphragm, the out of plane bending is allowed. Just in the direction of the in plane of that physical plates, the stiffness of that diaphragm would be taken infinitely high. So in RAM structural system, you can define the transfer slab both with those rigid as well as the semi-rigid criteria. Now, another important point which most of our user asks, and or the answer to that question would rather decide for the selection of the rigid or the semi-rigid diaphragm. Now, for the rigid diaphragm, first of all, as I mentioned, even though if you're meshing it, for example, in RAM structural system, all those internal nodes of the meshing would be taken as a consolidated one for the in-plane action of that floor, and the degrees of freedom for each floor would be taken as taken with the number 3. That means two in-plane lateral action, and one is the rotational degrees of freedom. But if it is a semi-rigid, then every nodes which are created from that meshing would carry its own degrees of freedom. So the answer is like if you're considering the rigid diaphragm, essentially the program is going to run the model much more faster compared to the semi-rigid one. Now, when you are using the semi-rigid one, then your question comes like, okay, what is the mesh size we take? Because you need to decide that, okay, what is the trade-off in considering the mesh size? So there is no such hard and fast rule to give you the exact number. Like, okay, at that point you need to stop meshing and you need to pick the result. That all depends on your experience. Now, while you perform the meshing, the internal nodes are created. So more the internal nodes are created, the better the result can be expected. But at the same time, your computational effort also get magnified. You need to invest a lot of man hours. You need to stress your computer because it will consume a huge amount of your computer resource like RAM and processing speed and all. So it will engage your computer. So you need to just strike the balance between the result that you are getting and the density of mesh that you can afford in your structure. So the best way is like you need to perform the mesh first with a very standard division. In most of the cases for a building like structure, it is like 10 by 10 mesh for a standard floor size is good enough. So just go for the analysis and you see the result. Now you just note that result and then you go for the next set of division. Next time maybe you are splitting that 10 division into a further 20. If it is too much stressful, then you can start with the fourth division, then eighth division, just like this. So note the result of every division size and then compare it with the next level of mesh density. Now you just compare the difference between the two consecutive meshing. If it is within the allowable limit, say for example, if it is having the value of 1% and 2%, and if you think that okay, that can be accepted, then you can stop doing any further meshing. So the whole idea is like you need to know that okay, at what point you can stop the meshing by judging the difference between the consecutive result and compare it with your acceptable limit. So that is the way you can just strike the balance between the mesh density and the result that you are going to use for your design. So the entire conclusion of this discussion to judge the different benefits and the different pitfalls of the rigid and semi-rigid, we can conclude it like this that the semi-rigid is the realistic and the most accurate way to capture the behavior of any kind of diaphragm, irrespective of any codal requirement. That means you can model any kind of floor system by physical plate elements, mesh it, and perform the analysis. But that would take a huge amount of time. So the rigid and flexible floors are two extreme conditions. So they are not the actual condition, but theoretically we take these two as an extreme condition. The reason for consideration of these two extreme conditions are to facilitate faster and getting the numerically stable computational performance. And finally, the use of the engineering judgment by assessing the benefit and the effort involved in modeling and analyzing the overall analysis runtime when the diaphragm qualifies for the both rigid as well as the semi-rigid condition.